Okay, so we've talked about different types of probability, but we're going to take a minute and go back to the fundamental counting principle and talk about number of outcomes. Okay, so let's review the fundamental counting principle. I know that we've done this before in previous videos, but we're going to be using it so much here that I think it's really important to review it. So the fundamental counting principle once again, it tells us that if two events, or if we'll start with one event, if one event occurs in m ways, and a second event occurs in n ways, then the two events together occur in m times n ways. So let's just take an example. If you are choosing outfits, we said if you have 3 shoes, 2 jackets, and 3 hats, then we can figure out how many different ways you can combine it by doing 3 times 2 times 3. Okay, or if you're going outside and you have 15 outfits, so choosing an outfit is the first event. 3 pairs of shoes, 2 jackets, and 3 hats. This is telling you is that you have 15 times 3 times 2 times 3. We multiply that, that's 270 ways of getting dressed. By contrast, if you have 6 entrees, we'll go back to the menu. 3 appetizers and 2 desserts. That means that you have 6 times 3 times 2, or 36 possible meals. Okay, and so what we're saying is that for each outfit, there are 3 different pairs of shoes that each outfit could be paired, can be paired with, and that would give you 45 different possibilities there. And then for each of those 45 possibilities, there are 2 different jackets that could be paired with each one. and then that would give you 90 possibilities. And then for each of those 90 different combinations, you would have 3 hats that could be paired with each of those. So that's where you get this 270 from. And then same thing here. Notice our order doesn't matter. Okay, you might eat an appetizer first, but I put it second here. It makes no difference. For every entree that you eat, you could order one of 3 appetizers to go with it. And then for every combination of an entree and an appetizer, you can order one of 2 desserts. So we have 18 possibilities with the entree and the appetizer. And then for each of those, we have 2 desserts. So it's 36 in total. And that's where we're getting, that's essentially what we're saying about the fundamental counting principle. Okay, so here's why we care about that. We can talk about something called permutations. So a permutation is a special use of the fundamental counting principle. So it's a permutation is an arrangement in which order matters. So we can think about different things where if we rearrange it, we're actually changing things. So easy thing to think about it is like a combination lock, which by the way should really be called a permutation lock. I have a feeling that maybe the creators of combination locks didn't really know what combination meant versus permutation, but it should be called a permutation lock. If you think about it, if you take your combination lock, if you put most combination locks have like 3 or 4 numbers that you put into it. If you put the numbers in it in the wrong order, it comes out, right? It won't open. Your ATM PIN number, that would be an example where order matters. If you enter the numbers in a different order, you won't be able to get money out of your ATM. So these are some examples. So combination lock, anything that has some sort of code, your passwords, right? Order matters there. So combination lock, this should be called a permutation lock. Any ATM PIN number we said would be another one. Any password would be another one. These are all permutations, order matters. If any of you have ever went to a big fancy party, you might get when you walk in, you might get a table arrangement, a table placement card, which tells you what table you're sitting at, or you might sometimes you get assigned even a very specific seat. Okay, so like if you go to a wedding, most of the time they do table arrangements, and that's because like there are certain people in your family, right, that you don't want to sit next to, and that maybe people don't get along, so they want to make sure that some people don't sit next to one another. So they use these table arrangements. They do these table arrangements to make sure that that doesn't happen. That would be another example of a permutations. These are all examples where our order really does matter. If we take letters, we care about the order because the order of the letters will create certain words, right? So again, another example of a permutation. So let's talk about how to calculate permutations. So think of it as the same event occurring multiple times. So let's write that down because I think it'll be really helpful when we think about how we're calculating it. And it's essentially what's going on, right? An ATM PIN number, we're taking a number and we're choosing numbers 4 times over. So when the same event example of the ATM PIN number. Okay. Let's ask ourselves, how many ATM PIN numbers are there? So a PIN number has 4 numbers to it. So what we're going to do is we're just going to draw a blank for each event. So each blank represents an event. Essentially what we're doing is we're simplifying the tree diagram so that we don't have to draw out the whole tree diagram. And now we're going to ask ourselves, well, how many outcomes are there for the first event? Well, for the first digit of your PIN number, there are 10 different outcomes, right? You can have the numbers 0 through 9. So that 10, this 10 here, is the number of outcomes for the event. So for the first digit, there are 10 possible outcomes. Under here, I'm going to put what the outcomes are. So your possible outcomes are 0 to 9. So I'm doing that here. You don't have to do that. I'm just putting it in so that you have it. These are the possible outcomes. So above the blank, we're putting the number of outcomes, and then below, we're just putting the possible outcomes. Now let's go and look at the second digit of your PIN number. So the second digit of your PIN number, again, could be 0 through 9. So we can repeat. We could have, some of you might have a PIN number that starts with a 77, okay? You could have a PIN number that's 0000. Don't do that. But your PIN number, it could be 0000, meaning we can repeat the same number multiple times. So there are 10 possibilities for the second digit. And then for the same reason, there are 10 possibilities for the third and 10 possibilities for the fourth. For each of these, the possible numbers could be 0 through 9. Okay, so each blank represents an event. Each blank represents choosing a PIN number here. That's our event. Sorry, choosing a digit of the PIN number. That's your event. This is the number of outcomes. You have 10 digits to choose from. And then we have 4 possible digits, so we have 4 events. And what do we do in order to calculate? We multiply. This is the fundamental counting principle. We have 4 events. Each one is happening in a different number of ways, or the same number of ways. And to get the total number of ways, we multiply. Fundamental counting principle. Think of it as your tree diagram, right? Tree diagram would be huge here. You would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then from each of those, you would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then from each of those, you would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then from each of those, you would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we have here is if we do 10 times 10 times 10 times 10, this is equal to, I'm going to write this again down here, 10 times 10 times 10 times 10 is equal to 10,000 possible PIN numbers. Okay, so we have 10,000 possible PIN numbers. So if you go to an ATM and you have somebody's debit card and you think, oh, I'm going to be able to just get in. You think, oh, I'm just going to be able to get in and get money from this person. Well, you have to try 10,000 possible PIN numbers. Okay, that's a lot of PIN numbers. It's going to take you a long time, which is why we always try and think of, not we, because I don't do this, but if you're trying to figure out somebody's PIN number, you would think about, oh, well, maybe a birth date or something, because otherwise you have to try 10,000 possibilities. Okay. You can also think about a license plate. So another example. Now, license plate order matters. And in this case, there are 6 different pieces to license plate. Six characters. The first 3 are letters. This is typical. It's not, I mean, different states have different things, but in New York State, typically the first 3 are letters, and the last 3 are numbers. Here we have 6 events, which is why we have our 6 blank spots. And we want to figure out, okay, how many possibilities are there for each event? Well, if the first 3 characters are letters, there are 26 letters in the alphabet. So the first 3 are going to be 26. I don't know why I wrote 20. I meant 26. And that's because you could have the letters A through Z for each of these. Okay. We're saying that there are 26 letters in the alphabet. Again, the part that I'm putting under these blanks is just for your benefit. Typically, you wouldn't write that. 26 letters in the alphabet. And then the second 3, well, there are 10 digits. So there are 10 possibilities for each of these. And the reason for that is that we have the numbers 0 through 9. There are 10 digits. That's where this comes from. And so if we want to count this, we want to figure out how many possible license plates there are. We would just do 26 times 26 times 26 times 10 times 10 times 10. And you can see how huge this number gets if we go and we actually calculate it. Sorry about that. I mean, look at it, how huge this number is. Now I'm just going to do 10 to the third because 10 times 10 times 10 is 10 to the third. So we can see that there are 17,576,000 possible license plates. Okay, which Again, it makes sense because every person who owns a car needs to have a different license plate. So if this is the way that they do it in New York, this gives you 17 million different license plates. Okay. And if they do it a little bit differently, where they change the order, where maybe in another state they do a letter and then a number and then a letter and then a number and then a letter and then a number, notice it wouldn't change. Okay, you would still have 17 million because ultimately you have 3 letters and 3 numbers. The order in which you're multiplying is different, but that doesn't matter for multiplication. Okay, but you might have 2 people with the same license plate, but because one says New York and one says New Jersey, it's different. Okay, but this does give you a tremendous number of license plates to choose from. Another example would be a password, right? If you have a password, if you notice now they're asking you to have your password so that you have uppercase and lowercase, and you have numbers, and you have special characters like an exclamation point or a number sign. All of this is to increase the number of possibilities for each of these, right? So it might be that for each character, you have not just 26 possibilities because you're not using every letter, because you're not only using letters, but just even between the uppercase and the lowercase, you have 52 possibilities because you can have an uppercase A and a lowercase a, and then add to that the 10 numbers. Well, now you have 62 possibilities for each one. And then add to that special characters, and now you have, 72 possibilities. Well, if you take 72, and most of these passwords, they say you must have 8 characters. If you take 72 and multiply it by itself to the 8th power, right? You're doing 72 times itself 8 times. So we're talking about 72 to the 8th power. Look at how many possible passwords there are. Okay, this isn't in just the millions. This is 722 trillion possible passwords. There's no way a person could sit there and try every single password. You'd be trying for the rest of your life without sleeping or eating or doing anything other than sitting at a computer trying all of the different possible passwords. This is why you would need a computer to break a password, okay? And this is why they encourage all of that, okay? The difference is if you just had letters and that's it, and there were no difference between an uppercase and a lowercase, you still have a lot and a lot of possibilities, but look at the difference. It's by magnitude. It's 208 billion. And this is if it's all letters. If we just went to, those 4 numbers that we had from the PIN number, we know it's only 10,000. So you can see why it's so important to create these passwords that are really strong, and why it makes it stronger when you have all of these different characters, because it makes it so much harder for even a computer to break it. A computer to go through a billion different possibilities, it's not that bad, but as soon as you get to a trillion or quadrillion, now it starts to take a lot more time, Okay. So these are types of permutations, but in each of these permutations, we have the possibility of repetition. We can repeat a letter. We can repeat a number. Then we have permutations where we don't have repetition. So these were all examples. With repetition. So you can choose the same letter twice. I'll say more than once because you can choose the same letter 3 times. Okay, let's take another example. Okay, let's take an example without repetition. are two monkeys. They're very attentive. They're looking really carefully at the lesson, listening carefully, but they're also playing in the background. So they're playing with these Legos and they want to create a tower. So they're going to stack them. So we have a red, yellow, a blue, yellow, blue Lego, green, and that it looks kind of yellow in my camera, but it's actually an orange Lego. Okay, let's take a look at all of the different ways that it could be arranged. So they could take these Legos and they could stack them. And they could get stacked like that. That would be one permutation. But we could take them apart and we could stack them in a different way. All we did was just change the yellow from the top, or the orange from the top to the bottom. Okay? That changed the whole permutation. Now we have a tower with a different permutation, okay? But notice it's the same event each time. When we do this, we start with one Lego. So we might start with the blue, and then we're saying, okay, we start with the blue. Well, how many possible Legos could go on top of it? Well, there are three possibilities. There's orange, green, or red. So we put the orange on top and we say, okay, well, now how many possibilities are there for the next Lego? Well, now there are only two. There's just green or red. How many possibilities are for the last Lego? Well, there's only one possibility. It's got to be red. And here's our tower. Okay, let's try this again though. So we're taking apart the Legos. How many possibilities do we have for when we start our tower? Well, now we have 4 possibilities. We had blue, orange, red, or green. Okay, let's say that we have orange as our first. Now we're saying how many possibilities are there for the second? Well, there are 3. We could either have green, red, or blue. Let's say that we choose red. Okay, well now we ask how many possibilities are for the next one. Well, we have blue or we have green. So now we have 2 possibilities. And now we have the last one. Well, the last one, there's only one possibility. There's only one Lego left over, and that's green. So now we have a tower. Each of these towers are different permutations, okay? So let's write this down. Here are monkeys listening again. So what we're doing here is we're creating a tower. With 4 Legos. 1 green. 1 orange. 1 red. And 1 blue. Well, we could go through and use a tree diagram to figure out the total number of possibilities. We have a red, a green, a blue, or an orange. This is our first event. The first Lego that we could put into our tower. for each of these, we have different possibilities. For the red one, we could choose to have green next. We could choose to have blue next. Or we could choose to have orange next. This is without replacement. We can't reuse the red, okay? That's what we mean by with repetition or without repetition, or with replacement and without replacement, okay? We can't reuse the red. Now, we can do the same thing for each of these. The difference is that if we use the green, we can't reuse the green. So we can use the red here. We could use the red if we do the blue first. And we could use the red if we do the orange first. For green, we can use the blue if we want to. We can't use the blue if we already used it. So we're not going to put blue as a possibility. But we can use the blue if we have the orange. Green, we can't use the green here because we already used it. But we can use the green as a second possibility here. And we can use the green as a third possibility here. For the green, we have red and blue already. We can use the orange as another possibility. And the same thing if we did the blue first. We can use the orange as another possibility. Okay. Well, now we have the first two Legos. We could have a red and a green. And what that means is that we could have a blue as the third Lego. Or we could have the orange as the third Lego. Because those are the two that we haven't used first. That we haven't used yet. If we had a red and a blue, then instead we could use an orange for the third Lego. Or we could use a green for the third Lego. And if we did a red and an orange, then for our third Lego, we can use a blue. Or we could use a green. And if we keep going with these branches, this did not. For some reason it's not switching colors, but you get the idea. We can also use an orange. Okay. We can't use the orange here because we already used it. And let's just keep going with these because we're not going to be able to get the whole table, the whole tree diagram into this small space. Over here, we used a red, a green, and a blue. So for the fourth Lego, it would have to be the orange. Here we used our next one, we used a red, a green, and an orange. So the next one would have to be a blue. Here we used a red, a blue, and a green. So again, the next one would have to be an orange. Here we used a red, a blue, and an orange. So the last one would have to be green. Here, same thing, we have a red, an orange, and a blue, so the last one would have to be a green. And then finally, for this last one, we used a red, an orange, and a green, so the last one would have to be a blue. And we can continue the other trees. We can continue for these where we do, here we have a green and a red. So the next Lego could be a blue or an orange. And then from each of those, we would have whichever Lego is left over. And what we can see here is that in the first one, we have 4 possibilities. In the second one, we have only 3 possibilities because we already used the red. In the next level, for each one, we have 2 possibilities. And in the next one, we only have 1 possibility because each time we used something that we had. So we had 1 less thing. So if we write this out in terms of our events like this, which is much faster, right? The first possibility would have 4. We could have a red, a green, a blue, or an orange. But what that means is that we've used one of them already, so for the second event, we only have 3 possibilities. Whichever of these 3 colors we didn't use here, that's what we could use for the second one. And what that means is that for the third time that we choose, we only have 2 possibilities because we already used 2 of these, so there are only 2 left. And finally, for the last one, there's only 1 possibility. Which means that there are 24 possible towers just from these 4 Legos. And I'm going to add up here. We're not just talking about repetition, we're talking about replacement. It depends on the type of situation, right? Whether you would say repetition or replacement. Here, we would typically say repetition because we're not pulling something out and then putting it back in. Whereas here, we would be talking about replacement because we would be taking a Lego out and then putting it back in. But here, we're using it for the tower, so we can't do that. Okay, so there are 24 possible towers here. Okay, so what does this mean? So in terms of just figuring out in general. So let's take another example. First of all, this 4 times 3 times 2 times 1. This is 4 factorial. So you would say it as 4 factorial. So we've talked about this a little bit on the very first day of class. I introduced this word to you. Some of you were familiar with it. 4 factorial is 4 times 3 times 2 times 1. Okay. If we talk about any number factorial, so let's just say n factorial. What we're doing is we're saying you're doing n, then you're multiplying it by the number that comes right before it. Then you're going down one other number. And I'm going to put a dot, dot, dot here. We don't know how many numbers there are. And then we just keep going until we get to 1. So just as some examples, 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial would be 3 times 2 times 1. 10 factorial would be 10 times 9 times 8, all the way down to 1. So that dot, dot, dot just says keep going until you get to here. So it's just a substitution for all the numbers in the middle. Okay, so here's why that's important. That's important because whenever we're talking about arrangements and we're using all of the things that we have, so we have 4 Legos, we're using all of them. Well, there are 4 times 3 times 2 times 1 possible towers. Okay, if we are using people, so let's say that we're trying to create a different group of people. So, okay, so my computer crashed, so I'm not exactly sure where this left off since I stopped the video. So I'm gonna do a little bit of repeating. So for example, let's take an example where we have 4 students in a group and each of them are being given a different role. So if you were in high school, some of you may be familiar with some of these roles, group roles, if you ever did any group work. You have a facilitator, a note taker, a timekeeper, and a devil's advocate. For those of you who don't know what a devil's advocate is, it's somebody who is essentially taking the opposite side and trying to get you to explain why you're correct. So we want to know in how many different ways can we form this group of 4. So we have 4 students. How many different ways can we form this group of 4? Here, order matters. The reason that order matters is that everyone has a different role. Think of it similar to the Legos. Each person is different. Okay, so we're taking those 4 people and we're putting them off to the side, and we have our 4 empty chairs. Okay. Now for the first, this is your facilitator. So this is each chair belongs to a different role. This chair would be whoever is your note taker. This chair would belong to whoever is your timekeeper. And this chair would belong to whoever is your devil's advocate. For the first chair, there are 4 possible people who we could put into that chair. Any one of the 4 students. We haven't assigned them a role yet. So any one of the 4 students can be placed into that first facilitator chair. There are 3 students left over, okay, who could be the note taker. 2 students left over who could be the timekeeper. And 1 student left over to be the devil's advocate. That would be the last student. So we have 4 times 3 times 2 times 1, or 24 possible ways to arrange these 4 people. Or 24 ways to assign the roles to these 4 people. Let's just make this simpler. Let's say suppose we had 10 students. And 10 seats. How many permutations are there? Okay. Well, again, each one represents an empty seat. So for the first seat, there are 10 possible people who could sit there. 9 for the second, 8 for the third. I don't know why I wrote 3. 7 for this one, then 6, 5 people left to choose from. 4, 3, 2, 1. The other way that we could write this is just 10 factorial. Suppose that we're not seating everybody though, okay? Suppose we only seat let's just seat 5 of the 10 people. So if we only seat 5 of the 10 people, then what we're doing is we're saying we have 5 seats. Now for the first seat, we still have 10 possibilities. 10 people can sit in the first seat. 9 in the second, 8 in the third, 7 in the fourth, and 6 in the fifth. And if we want to know the total number, it's just 10 times 9 times 8 times 7 times 6. So here's our calculator. If we want to do 10 factorial, you can see that it's 3,628,800. Okay, but if we only want to do 10 times 9 times 8 times 7 times 6, we have to do all of this work. Okay, there's a shortcut for this. We don't have to actually write out 10 times 9 times 8 times 7 times 6. What we're doing is we're doing 10 factorial, but we're saying leave out the last 5 terms, okay? We don't want the last 5 terms. Cancel them out. And in order to cancel something out when we're multiplying, we have to do the opposite. We have to divide. So what we're doing here, what this is really equal to, is it's another way of doing 10 times 9, which is a long way to write it here, but we have a shortcut. I just want to show you what's happening. We're doing 10 times 8 times 9 times 8 times 7 times 6. But if we want to use factorials, we can. And what we're doing is we're saying, okay, but take out the 5 times 4 times 3 times 2 times 1. Because notice what's happening. This is all canceling. The second half, it cancels. Right? That goes away. And the advantage of this is that instead of writing 10 times 9 times 8 times 7 times 6, we can write this as 10 factorial over 5 factorial. And we don't have to type all of this in. So if we had 100 people, okay, then instead of writing 100, and let's say that we had 100 people and we were seating of them. Well, in that case, this becomes really long, right? We have I think this is 25. Now this becomes really long to start filling in. We know that we have 100 times 99, But this becomes really, really long to fill in. So instead, what we're going to do is we're going to do 100 factorial. And we know that we're going to cross out everything that comes after the first 25. So we're going to subtract 25 from there. And that's the factorial that we're going to cancel. So like this was 10 factorial. And then what we did is we subtracted 5 from it. We subtracted 5 because that was how many numbers we did. We had 5 numbers. So we subtracted 5 and we said, okay, now we'll cancel out everything else. So we're doing the same thing here. We have 100 numbers. We're subtracting 25 of them because the first 25 we're fine with. And we're going to cancel out whatever is left over. Okay? So this would be 100 factorial over 75 factorial. And this is a lot faster to write for us than if we tried to write 100 times 99 times 98 times 97 and so forth. Okay? Now because of that, we have a formula for permutations. So the number of permutations if we have n things to choose from. So I say things because sometimes it's not people, sometimes it's Legos. So n things to choose from. And we're choosing x of them. So instead of seating all 10 people, we're only seating 5. Here, instead of seating all 100 people, we're only seating 25. And I'm going to put with no repetition or replacement. The way that we write this is NPR. And I'll put that down in a second. This is n factorial. So if we have 100 things, there are 100 factorial ways of choosing all of them. But we're only, sorry, this should be an X, not an R. But we're only choosing X of them. So we're canceling out everything else. So we have n factorial over n minus x factorial. Okay, so the P that just tells us it's a permutation. N is the number of things we have. And X is the number of things we're choosing. So for example, 30p2 is 30 factorial over 30 minus 2 factorial, or 30 factorial over 28 factorial, which is the same thing as 30 times 29. And I like to think of it this way because in most cases you're not choosing that many things. So this says of the 30, we're choosing 2 things. In the first case, we have 30 choices. In the second case, we have 29 choices. In other words, essentially what we're doing is we're doing 30 factorial, but we're saying SAP after 2 things. So we're doing 30 factorial, but we're stopping after 2 numbers, where the 2 is our x and the 30 is our n. Okay, so this is saying we have 30 things, but we're only choosing 2. Now, because of this, there's some things that we could say about NPR. If n equals r, then NPR is just n factorial. Okay, in other words, we're choosing everything that we have. If we have 4 Legos, we're using all of them. If we have 100 people, we're seating all 100 of them. It means something else too. N can't be less than R. Okay, because we can't choose more than we have. And just by definition, if we're choosing nothing, we're saying that there's only one way to do that, and that's just choosing nothing. So this helps make sure that we don't wind up with anything undefined. If we choose nothing, there's only one way to do that. So NP0 is equal to 1. It doesn't matter what n is. Okay, so just some examples. 6 P4 would be calculated as 6 times 5 times 4 times 3. Notice we're doing n factorial and we're stopping after 4 things. This is because we have 4 blanks, okay? But the other way of calculating that is 6 factorial over 6 minus 4 factorial. It's like doing 6 times 5 times 4 times 3 times 2 times 1, but we're canceling out the 2 times 1. That's what the division by 2 factorial does. Now, typically when I calculate permutations, I'll do it this way. I'll just do 6 times 5 times 4 times 3. The times when that doesn't work is when your n is huge and your r is also really large, okay? But if we take, let's say, 8p3, so we have 8 things and we're choosing 3 of them, whatever those 8 things are, so here we're only choosing 3 of them. And you can either write this as 8 factorial over 5 factorial. But again, for me, I actually prefer just writing it as 8 times 7 times 6. Okay, but this formula is saying you're doing 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, but that 5 times 4 times 3 times 2 times 1 is canceling out. Okay, so this is what you're left with. So this is permutations. So I'm just going to start talking about combinations here, but we're going to talk about it a lot more in the next lecture. I'm just going to define it. So a combination is an arrangement in which order doesn't matter. Blue, red, green is the same as green, red, blue. And this is the same as red, blue, green. All of these are equal. Okay? There is no difference. So what we're saying here is there is only one combination of the colors red, green, and blue. But we know from earlier that there are 3 times 2 times 1 permutations. This is like with the Legos. Okay, because we have 3 slots. In the first one, we could have red, green, or blue. In the second one, we already used 1, so we would only have green or blue. And then in the third one, we used 2, so we would only have whatever color is left over. So there are 6 permutations, but there's only 1 combination. So this is a big difference between combinations and permutations. And what this should tell you is that the number of combinations is always less than the number of permutations. Okay, so in the next lecture, we're going to be talking about that primarily and how we would calculate the number of permutations. And then we'll take a little bit of time and just talk about how we might use this in probability. Okay, and so that's it for this one. We have 4 students. This is another example, a different example. We have 4 students.